continue with examples for 4.3. For question number A, we have the quotient of any two rational numbers with non-zero divisor is going to be a rational number. So our assumptions is that we're going to have two rational numbers. So R and S are going to be rational numbers. So the definition of that assumption, step number 2, will be that R will be represented of the form P over Q and S, I don't know, A over B. And because they're non-zero, and in particular S is not zero, then we're going to have that A is not zero. Okay, so we have A not zero, Q is not zero, and B, of course, is not going to be zero. Now, if we check for the quotient of R over S, then what we're doing is really checking what is P over Q over A over B. We can simplify this by multiplying the streams in the middle. So remember that by properties of the division, a fraction, this is P times B over Q times A. Okay. And now, because we have that Q and A are different from 0, then Q times A is going to be different from 0. Notice here, this is our third step, the manipulation. But now, because P and B are integers, Q and A are integers, then we're going to have that this is integer, and this is different from 0. Then this step is pretty much giving us our definition of the conclusion, which is our step 4. And so finally, we can conclude that R over S is just going to be a rational number. Okay, so let's talk about some true and false questions. This is the sum of two irrational numbers is always going to be irrational. This is not true. In particular, if you consider the irrational square root of 2 and the irrational minus the square root of 2, the sum of these two is going to be 0, and 0 is actually a rational number. So the irrationals are not close. The product of a non-zero rational and an irrational is always going to be an irrational. This is true, and this was actually something that we're going to prove later. Once that we have the proof that a square root of 2 or square root of 3 is an irrational. For now, this is true, and we're going to be proving that later. Okay. The argument is a little bit difficult to make at this point. Will require truth by contradiction. So just have that in your mind, because we'll come back to this statement. Now, between two rational numbers, there's always another rational number. This is true. In particular, consider R and S rational numbers. This is our assumption. So by essentially, they're both rational numbers. We can always do R plus S. That's going to be a rational number just because the rationals are close. And also, we can have R plus S divided by 2, which is going to be still a rational number because this is, once again, close under the rational number. So the product or division of any rational numbers is a rational number. But now, notice that R plus S divided by 2 is going to be between R and S. So let's assume that R is less than S. You're going to have that R plus S divided by 2 is in the middle of those two. Okay? So that is the way to prove this. And if you're wondering how did you get from the inequality, you can always start from R less than S and then add R on both sides. So you will get 2R less than R plus S. And so that way you get that R is less than R plus S over 2. Or you can also do sum of 2S. And so R plus S is less than 2S. And so R plus S divided by 2 is less than x. And so in this way, you get this inequality here. In terms of proof, of course, there are multiple ways that I can say that I'm doing here. The definition of the assumptions, the manipulation is the inequalities, and then from the conclusion is the fact that I have something in the middle of that inequality. So you can structure that proof in the 5 steps. It's just it was kind of easier to do it this way for now. But you certainly can arrange this in the 5-step way. I encourage you to try it on your own and do it. Now, for question number 10, we got to prove that if r is rational, then r squared is also irrational. And we're assuming that r is different from 0. Well, if r is irrational, and this is our assumption, the definition of the assumption will be r is equals p over q, where p and q are rationals, and q is different from 0. Then our manipulation step is going to be r squared, which is going to be p squared over q squared. And notice p squared and q squared are going to be integers, and q squared is going to be different from 0. So this is pretty much our definition of the conclusion. And so the conclusion here is that r squared belongs to the rational numbers. Also, another way to prove this is that because product of two rationals is rational, then r plus r is going to be irrational. So this is another way of proving that r squared is going to be irrational. Now, to prove that, or to explain why 3 over 0 is not irrational and not irrational either, well, first than anything, the big problem is that division by 0 is not defined. So this is not even a number. 3 over 0 is not a number. And if it's not a number, then overall, it cannot really be anything, rational or irrational. Now, for question 12, we have check if the following statement is true, prove it if false. Prove it if false, give a counterexample. If x and y are rational, then x plus y is irrational. We actually recently did counterexample for something similar when we were using x equals the square root of 2 and y equals minus the square root of 2. Notice that x plus y was 0. That belongs to the rationals. So this is actually a false statement. And this is the counterexample that shows that this is false. The sum of two irrationals will not give me an irrational. Now, let's show that point 1, 2, 3, 1, 2, 3, 1, 2, 3, repeating 1, 2, 3 is irrational by finding the integers that give me the fraction. Okay, so once again, this can be represented as 0, 1, 2, 3 periodic. Because we have 3 decimals after this point, what I'm going to do is I'm going to be multiplying by 1,000. And so if I multiply by 1,000 x, then I'm going to have 1, 2, 3 here, dot 1, 2, 3 periodic. And so the advantage of that is that I can subtract this 2 and I can get rid of the periodic part. So 1,000x minus x is just going to be 123, 123. And so this is going to be 999x equals 123. And so pretty much x equals 0.123 periodic can be seen as 123 over 999. You can actually simplify this, and this is going to be 41 over 333. So you pretty much can divide this by 3. For question 14, we want to prove that if we have rational numbers and r is less than s, then this is a rational number so that it's between those. We actually proved this very recently, kind of did the same thing that we were doing before, where we just consider that if r was, both rational r was less than s, then we could do the sum r on both sides. And so we get 2r less than s plus r. But you can also do r plus s less than 2s, adding s on both sides. So in here, add r, add s. And so notice that you get r s plus r over 2. And here you get r plus s over 2 less than s. So you're going to end up having with these two that x plus r over 2 is actually in the middle of r and s. And then the thing is, you got to prove that s plus r over 2 is irrational. But because x is irrational and r is irrational from the assumptions, then s plus r over 2 is actually going to be irrational. And so with this, you can prove that there's another rational in the middle, and this is the idea of density, which shows that between two numbers, there's always going to be another one in the middle. Now, for question 15, we have all real numbers are rational. And the proof is every real number can be written as a decimal. Decimals are quotient, therefore all real numbers are rational. Well, the issue here is this statement that every real number can be written as a decimal. This is false. And so if we start from false, we can go in whatever direction. But like you have things like pi being 3.14, 15, 9, so on and so forth. Those are irrational numbers. Also square root of 2, which is like 1.41, 4 to 1, and they continue, and they don't have any pattern. So those are irrational numbers. So not all the real numbers, these are real numbers, by the way, and not all the real numbers are going to be rational. Okay, so with that, we have a couple of counterexamples out of the way. So this finish the examples for section 4.3.